So I want to remind you all that in the first quadrant, all the trig functions are positive. In the second quadrant, the sine function is positive, and the other two, cosine and tangent, are negative. In the third quadrant, tangent is positive, and the other two are negative. In the fourth quadrant, cosine is positive, and the other two are negative. And of course, if sine is negative, cosecant is negative. If cosine is positive, secant is positive. If tangent is negative, cotangent is also negative. But all the reciprocal functions have the same signs. So now, what I want to do is drop my pen. Not really. What I want to do is look at this example. So here we have sine of theta is equal to 7/8. We know that cosine of theta is negative, and we're being asked to find tangent of theta and cosecant of theta. And so there's a couple things we need to do. First thing we need to do is we need to figure out what quadrant the angle is in. So if sine is positive, that means I'm either going to be in quadrant 1 or quadrant 2. Right? I'm thinking, okay, all students take calculus. If sine is positive 7/8, I know I'm either in quadrant 1 or quadrant 2. But if cosine is negative, I can't be in quadrant 1 because all trig functions are positive there. So it's got to be quadrant 2. So I know I'm in quadrant 2. And in quadrant 2, tangent's going to be negative. Cosecant's going to be positive. Cosecant might have been a little too easy. I think I might have meant to ask for secant. We'll do secant as well. And then we need to draw the triangle. And usually when I draw a right triangle for an angle, I don't worry about the signs. I don't be like, oh, this side's negative, this side's positive. Like I know we did that in class yesterday when we were writing things in the different quadrants, but generally we're not going to do that. We're just going to say, I know sine is opposite over hypotenuse. So in this triangle, I'm going to draw the opposite side is 7, and the hypotenuse is 8. And then I'm going to find the third side by using the Pythagorean theorem. So let's call it x. We know that x squared plus 7 squared equals 8 squared. So that's x squared plus 49 equals 64. 64 minus 49 is 15. So x squared equals 15. And I'm going to say that x equals the square root of 15. And I'm not going to worry about the negative or positive. I'm just going to say it's positive. So I'm going to say x is the square root of 15. And then I'm going to use the fact that it's in quadrant 2 to figure out what tangent and cosecant and secant are. So tangent of theta is the opposite over adjacent. So it's going to be 7 over the square root of 15, which I should rationalize as 7 times root 15 over root 15 times root 15, which is just 15. Now, I know that since we're in quadrant 2, tangent is negative. So really this should be negative 7 over root 15, which is negative 7 root 15 over 15. And that's typically how I do it. I find the value first, and then I use the quadrant to determine if it's positive or negative. Cosecant's too easy, right? If we know sine is 7 over 8, we know cosecant is 8 over 7. So cosecant, real straightforward, just 8 over 7. And then secant, so again, I don't usually think about what secant is. I think about what the reciprocal cosine is. So I know cosine is root 15 over 8. So I know secant would be 8 over root 15. So secant of theta is going to be 8 over root 15, which again rationalizes as 8 root 15 over 15. What else do I need to do? I need to fix the sign, or at least I need to think about the sign, right? I know again, quadrant 2, cosine is negative, so secant is also negative. So this should be negative 8 over root 15, or negative 8 root 15 over 15. So that's how we do a problem like that. We draw the triangle, we use the information we have to determine the quadrant, and then we use the quadrant to determine what the positive or negative of each trig function is. All right. So let's move on. And maybe if we have time, which we probably won't, because I always go over. If we have time, then we'll do another example like this at the end. So let's talk about reference angles. We're going to use reference angles a lot. So reference angles. So what is a reference angle? The definition is a little bit wordy. I'm going to kind of abbreviate it. So the reference angle of an angle is the acute angle, meaning an angle between 0 degrees and 90 degrees, or 0 radians and pi over 2 radians. It's the acute angle we obtain when we drop a perpendicular to the x-axis. Perpendicular is my least favorite word to write. This is probably not the most official definition you've ever seen for this, but it works. More official definitions talk about if your angle is drawn in the standard position, meaning you start at the x-axis and you go around like this, then it's the left, it's what you get when you draw the arc from the terminal ray to the x-axis. We don't need all that language, right? This is definitely enough. And really, we just need some examples, and then it'll be ultimately clear what we were talking about. And then I don't want to go too fast. Definitely let me know if I'm, not that someone said that, I'm just like, I'm going kind of fast. I'll erase the back of the board while I give you guys a chance to write down whatever you want to write down. Also, in case you weren't aware, I am posting the videos of the class, although I posted yesterday's class kind of late today. I'll try and get this one posted sooner than that, like sometime this afternoon. I will post the videos of the class, and I already posted the lecture notes I'm working off of. So if you are looking for what happened but you missed it in class, it's definitely available on Canvas. You're also welcome to ask me via email or discussion, All right, so let's look at some examples. 120 degrees has, well, I'm going to draw it first. What as its reference angle? I'm going to abbreviate reference angle as ref angle, or maybe just RA after I get, after we've done it like 10 times. So here's how we're thinking about this. We're drawing the angle in the standard position, meaning we're starting over here on the positive x-axis, and we're just drawing out the angle like we usually would, which would be, probably a little too far. Again, your picture doesn't have to be like super exact. Really, you don't even have to draw a picture. The 120 degrees, and then the reference angle is what you get. I think about it like you can drop this perpendicular always to the x-axis, and then this angle here, that is your reference angle, which in this case is 60 degrees. And the way I think about it is, well, if you're going to the x-axis, if you're over here, this angle measure, if you've gone halfway around the circle, is 180 degrees. So you're really just kind of asking, how much more do I need to get from 120 to 180? The answer is 60. You can also do the subtraction, right? You can say, oh, well, if I want to find this angle here, I'm going to do this larger angle of 180 degrees minus this angle of 120 degrees. And that's going to give me this angle in red, which is 60 degrees. Oh, come on. Pen on the hand. Oh, well, it happens. So really, when I think about a reference angle, I think about the angle I need to get back to the x-axis. Either how much I have to add on to get to the x-axis, how much I have to subtract off to get to the x-axis. Or even over here, how much I have to add on to get to the x-axis. So let's do some more examples. Yeah, I can fit one in here. So what about the reference angle for 208 degrees. Part of finding the reference angle is knowing what quadrant you end up in. So, words, 208 degrees is definitely in quadrant 3, right? It's a little more than 180, but it's not as big as 270. Right, so here we have 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then back again to 360 degrees. So we are definitely in this spot right here. And so if that's, excuse me, sorry about that. If that's 208 degrees, now we're trying to measure back to the x-axis. So we're dropping perpendicular this way, or we're drawing this little arc this way. And to find that angle, well, again, that's 180. We're going to do our angle 208 degrees minus 180, which is going to give us a reference angle of 28 degrees. There's something else I want to say here. The way you calculate the reference angle, so I mean, you can kind of just think about it as I went 180 and then I went 28 more, and 28 is the reference angle. But you can also always do the math, right? If you're in quadrant 2, you're going to do 180 minus your angle to find the reference angle. If you're in quadrant 3, you're going to do your angle minus 180. And you'll see that if you subtract in the wrong order, you're going to get a negative answer. And we don't want negative answers. So if you get a negative answer, you're like, oh, I subtracted the wrong way. Obviously, I do something different. Okay, a couple more examples. Actually, not just a couple more, a lot more examples. Not going to lie. Got lots and lots of examples. And hopefully enough time to do them all. So much time, not really. Okay, so let's look at this next one. Keep my examples in order here. Also, please do stop me if you have questions, say something, type something, whatever. So, I don't know why I need to hold this, I don't. So let's find the reference angle for 330 degrees, which is definitely in quadrant 4. Right, that's 330 degrees. Again, I will mention I am drawing all my angles in the standard position. Right, we're starting on the positive x-axis and we're going in the counterclockwise direction, which kind of brings up something important. So we're trying to find this angle here. Again, I'm not always going to drop, right? You can drop the perpendicular to the x-axis. I don't really think you need to draw this to know which angle you're doing, right? I'm always really just starting at my terminal ray and then drawing the angle up to the x-axis. Never the y-axis, always the x-axis. I'm only going to say that like 100 more times. So we want to find this angle. You can either just eyeball it and say, well, I went 330. How much more do I need to get to all the way around? And the answer is 30 degrees. A lot of the reference angles, you're not going to have to do any math for, right? You could just see, oh, I need 30 more degrees to get there. You could also calculate it as 360 degrees minus 330 degrees, which is 30 degrees. So if you're in quadrant 4, the mathematical operation you would do to find your reference angle is 360 degrees minus whatever your angle is. Couple other examples. 45 degrees has a reference angle. I shouldn't say, there's only one reference angle for any angle. Has reference angle 45 degrees. So an angle that's already acute, that's between 0 degrees and 90 degrees, is already a reference angle. One different pen. Okay, fine. We'll also point out that 90 degrees does not have a reference angle. Neither does, I don't know, 180 degrees, 270 degrees, etc., etc., etc. Any of the angles that terminate on one of the axes doesn't have a reference angle. These angles are called quadrantal angles, which I think is just fun to say. I'm not going to pretend. I enjoy saying the word quadrantal as much as possible. These are quadrantal angles. And they do not have reference angles, but any other angle does. So I would like you guys to take a couple minutes and find the following reference angles. I should say. So find the reference angles for, what have I got here? Where'd you go? For a theta equal to 150 degrees, for alpha equal to 240 degrees, for gamma equal to 315 degrees. And, oh yeah, I'll do another. And for beta equal to 460 degrees. Okay, so go ahead and do each of those. I'll give you guys 2 minutes to work on that. After saying 2 minutes, I realized none of my time-telling devices in this room have a second hand on them. So it's been about 2 minutes, maybe not quite. Yeah, really, no, everything is like just the minutes. Okay, so would anyone like to volunteer their answer for theta equal to 150 degrees?
I got 30.
Me too. And you can either think of that as 150 degrees plus 30 degrees gets you to 180, or you could do 180 degrees minus 150 degrees. Someone else, would you like to tell me what you got for 240 degrees?
I got 60 degrees.
Yeah. And I imagine you either thought, right, you went around to 240 and you're like, oh, I'm 60 too far. Or you did 240 minus 180 is equal to 60 degrees. Somebody else? Don't be shy. You can type. I can wait. Thank you. Yes. Awesome. Great. Yeah. The reference angle is definitely 45 degrees. And you can even think of it again, right? You went 315. You need to go 45 more to get to the x-axis. Or you could do 360 degrees minus 315 degrees is equal to 45 degrees. And this last one is more than a full revolution. So you can either, when I have more than a full revolution, I just like to cut off the whole revolution. So I could say this angle, the technical word is coterminal with the angle 460 degrees minus 360 degrees is 100 degrees. So both of these angles end at the same ray. Right? If I draw them in the same position, so if I draw 100 degrees, it looks like this. Come on, kind of like this. Usually it's better than that. If I draw 460 degrees, it looks like this. But both of these angles terminate on the same ray. And so they both, since they are coterminal, they both have the same reference angle. So instead of finding the reference angle for this, I can say, well, oh, here it's obvious. Maybe not obvious, but it seems not too hard to figure out that the reference angle here is 80 degrees. And so it's going to be the same here, 80 degrees. Here, 180 degrees minus 100 degrees gets us to 80 degrees. Here, 460 degrees. First, you have to subtract the 360 to get to 100 degrees. And then you have to, that's not right, James. I mean, you can do it that way. That's kind of not what I really meant. If you really want to do the math, which I don't know, I think this is bad. But you could say, well, okay, this is 540 degrees. And then you could do 540 minus 460 to get 80. I don't think that's the way you should do it. I think this way is much better to say, I'm just going to find the smallest normal angle that makes sense to think about and then find the reference angle for that angle. Okay, so reference angles work just fine in degrees. It's usually not too hard to tell what quadrant you're in, and it's usually not too terrible to have to either subtract from 180 or subtract 180 or subtract from 360. Those are kind of the three things you have to do to find a reference angle if you're working with degrees. I'm gonna wear my voice out. Okay, so most of the time, we're probably going to be using radians for reference angles. Because most of the time, we're probably just going to be using radians in general. The nice thing is the idea of how they work is exactly the same. Right? It's still the same idea of you're trying to figure out what angle you need to get to the x-axis. It's just you have to remember how things work in radians instead of degrees. So let's look at some more examples. I'm going to switch the order of these. Let's look at, let's say our angle, theta, is, let's say, 7 pi over 9. Now I'd like everyone to type in the chat what quadrant this angle is in. I see no one typing in the chat. 4 is a good guess, but it might not be right. See some 2s, okay. We're gonna have to work on the everyone aspect of that, but I'll take your 2s for the moment. So yes, we are definitely in quadrant 2. And the way I think about this is halfway around is 1 whole pi worth of radians. 7 pi over 9 is a fraction of pi that is less than a whole pi. So I know that this is going to be, well, I guess it could be in quadrant 1, right? All I'm saying right now is that I know it's less than 1 whole pi. But I also know that 7/9 is more than a half. So I know I'm between pi over 2 and pi, which means I'm in quadrant 2. So I'm going to draw something like this. Maybe that's my angle, 7 pi over 9. And then I'm trying to find this angle here. So the mathy way of doing it would be to say, well, this angle is, so just like with degrees, right? If it was degrees, we would do 180 degrees minus whatever this angle is in degrees. It'd be 140 degrees. In radians, we would do pi radians minus 7 pi over 9 radians. Pi radians is 9 pi over 9 radians. Right, we did that so that we have a common denominator to actually subtract them. And then 9 pi over 9 minus 7 pi over 9 is 2 pi over 9. That is our reference angle here. Which again makes sense because it's how much more we need to get 1 whole pi. Right, I've got 7/9 of pi. I need another 2/9 of pi to get a whole pi. On board. Let's do some more examples. So the ideas are going to be the same. If your angle is in the second quadrant, you're going to do pi minus your angle. If the angle is in the third quadrant, you're going to do your angle minus pi. So let's look at the angle. What have I got here? 17 pi over 12. Now, usually the way I think about what quadrant the angle lives in also ends up often telling me what the reference angle is. So I know I'm bigger than pi, right? 17 over 12 is definitely more than a whole pi. It's definitely less than 2 whole pies, right? Because 2 pi would be 24 pi over 12. So I'm somewhere between here and here. But am I in quadrant 3 or am I in quadrant 4? Well, that's where I would break this up. I would break this up as 12 pi over 12 plus 5 pi over 12. To help me see that that's 1 whole pi. And is 5 pi over 12, or 5/12 of pi, is that bigger than half of a pi or less than half of a pi?
Less than.
Definitely. So this is less than half a pi, which means I went 1 whole pi and then not quite another half of a pi. So I'm definitely in the third quadrant. Now the thing is, this work also shows me what my reference angle is, right? I went 12 pi over 12. That's my whole pi right there. So there's 12 pi over 12. And then this part here, that's my 5 pi over 12, which is my reference angle. You could also do the work, right? You could say the reference angle is 17 pi over 12 minus pi, which is 17 pi over 12 minus 12 pi over 12, which is 5 pi over 12. That would also be a perfectly fine way of doing it. I'll reiterate here. Usually the hard part for radians is getting a good feel for which quadrant a radian, an angle measured in radians lands in. It can be a little bit more challenging and be like, I'm not sure if that's quadrant 3 or quadrant 4. So that's probably where you might have to do the most kind of practice for this. I don't know if I love that example there. Let's do it anyway. Yeah. Let's do 18 pi. So reference angle for alpha equal to 18 pi over 11. Again, definitely bigger than 1 whole pi. Definitely less than 2 whole pi. So we know we're somewhere either in quadrant 3 or quadrant 4. And again, I think it really makes sense to break it up into the 1 whole pi, which is 11 pi over 11, and then the 7 pi over 11 that's left over. So drawing the picture, again, picture not required. I just like to draw it to help me see what's happening. There's my 11 pi over 11. And then is 7 pi over 11, is that gonna have me end up in quadrant 3 or in quadrant 4? Well, is this bigger than pi over 2 or less than pi over 2? Which is it? It's a good question. It is more. The way so 7/11s, right? The previous one I think was a little easier because for the previous one, it's really obvious that 6 over 12 is a half. So 5 over 12 definitely is less than half of that. Here, since our denominator is odd, it's a little more challenging. But I know that half of 11 is definitely, well, 7 is definitely more than that, right? I mean, half of 11 is 5.5. And so 7/11s is definitely more than 5.5 over 11, which is more than a half. So we definitely have this, which means we're going to end up in quadrant 4 somewhere. And here, knowing that this is 7 pi over 11 might not be the most useful thing. It might be. But the way I would probably calculate my reference angle here well, I'm just trying to find this angle. So I know this whole angle is 18 pi over 11. I want to find out how much more I need to get to 2 pi. So I'm just going to do 2 pi minus 18 pi over 11. 2 pi becomes 22 pi over 11 after I multiply by 11 over 11 minus 18 pi over 11. 22 minus 18 is 4 pi over 11. That's my reference angle. Just as kind of something to be aware of, let's say we accidentally made a mistake. Let's say that we thought our angle was in quadrant 3. And so we said, well, okay, if it's in quadrant 3, I'm going to do 18 pi over 11 minus, I guess this might not be the best thing, minus pi is 7 pi over 11. If we said that was our reference angle, we would maybe then notice, oh wait, that reference angle is too big, right? This angle is definitely bigger than pi over 2, which is too big. So if you get a reference angle that's too big, it means you have probably imagined your angle terminating in the wrong quadrant. Okay. Yeah. Go ahead.
So when you mean it's too big, does that mean it cannot be greater than pi over 2?
Yes, every reference angle has to be between 0 radians and pi over 2 radians, or 0 degrees and 90 degrees. Or more concisely said, every reference angle has to be an acute angle. Okay. So now let's get to where we really want to get to, which is the angles we really care about. So while you will definitely be asked to find some reference angles of kind of strange angles like these, there's a certain list of angles that we really, really care the most about. And they're angles like this one. So 3 pi over 4. Actually, I'm going to write all these down, yeah. And 7 pi over 6. And 5 pi over 3. So the reference angle for 3 pi over 4, well, that's in quadrant 2. Right? I know it's definitely more than half of pi. It's definitely less than a whole pi. And the reference angle is pi over 4. Because those add up to pi. Here for 7 pi over 6, 7 pi over 6 is a little bit bigger than pi. It's going to land me in the third quadrant. And the reference angle here is pi over 6. And we can find that by doing 7 pi over 6 minus pi, which is 7 pi over 6 minus 6 pi over 6. Or you can just kind of see, right, I've got 7/6 of pi. I'm 1/6 of pi too big. So my reference angle is definitely pi over 6. Sorry, I didn't finish my subtraction here. And how about for 5 pi over 3? Well, that's going to end up in quadrant 4 because I'm more than 1.5 pi. And 1.5 is terrible, but right, there's a whole pi, 3 pi over 3. And then I've got another, this is 3 pi over 3 plus another 2/3 pi, or 2 pi over 3. And that's definitely going to get me like to about there. And my reference angle, well, again, I'm trying to get all the way over to 2 pi here. I need exactly 1 more pi over 3 because 5 pi over 3 plus pi over 3 is 6 pi over 3, which is 2 pi. I messed up my color scheme, oh well. But here's what I want you to know. For angles like this, angles that we care about, that are like angles that have special angles as their reference angles, right? So each of these angles has one of our special angles, pi over 4, pi over 3, or pi over 6 as a reference angle. Angles that have those angles as reference angles always have a certain look to them, which is going to make it really, really easy to know when you have a special angle as a reference angle. So here's, do I want to say this first? Yeah, I do. So here's the thing that's kind of great. These angles, I'm going to include the reference angle even though it's kind of silly. So pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3 all have pi over 3 as the reference angle. And actually, before I keep going here, let me show you. So I could draw this for you, but there's lots of great drawings of this online. So let me just share my screen for a second. And can I do that? Maybe that'll work. Does that look reasonably sized to everyone? Can you see that all right? Can I make it bigger? Ooh, I can make it bigger. Can you see it now? Hopefully, yes. So if we look here, here's pi over 3. Reference angle is definitely pi over 3. I wish I could, man, if I could draw on this, that'd be cool. There's probably a way to draw on this that I am not smart enough to figure out in the moment. 2 pi over 3, we measure down to the x-axis, we get pi over 3. 4 pi over 3, we measure up to the x-axis, we get pi over 3. And 5 pi over 3, we measure up to the x-axis, we get pi over 3. Now the cool thing is that it's true for the other types as well. For pi over 6 and 5 pi over 6 and 7 pi over 6 and 11 pi over 6, each of those has the reference angle of just pi over 6. And again, for pi over 4, for 3 pi over 4, for 5 pi over 4, for 7 pi over 4, each of those has a reference angle of just pi over 4. So the nice thing is, now this is only true for our special angles. But when you see one of these things that has a denominator like a special angle, so let me stop sharing for a second. Right, so pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4 all have pi over 4 as the reference angle. And lastly, pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6 all have pi over 6 as a reference angle. So here's the way I tend to think about it. If you have an angle measured in radians and it's reduced, the fraction has to be reduced. If the denominator is 3, 4, or 6, the reference angle is respectively pi over 3, pi over 4, or pi over 6. So if I give you something, right, I mean, this is the whole list of all of the angles we really care about. But if I give you something, like, for example, if I give you something that's more than a whole revolution, like, I don't know, 37 pi over 6, does 37 pi over 6 reduce? No. So since it doesn't reduce, I know automatically the reference angle is pi over 6. The other nice thing about this list is that they go in order by what quadrant they're in. So 1 pi over 3 is in quadrant 1. 2 pi over 3 is in quadrant 3. 3 pi over 3 reduces, so we don't care about it, right? That reduces to just pi, it's quadrantal. 4 pi over 3 is in quadrant 3, 5 pi over 3 is in quadrant 4. Same here, pi over 4 is in quadrant 1, 2 pi over 4 is just pi over 2, it's reduces, we don't care about it. 3 pi over 4 is in quadrant 2, 4 pi over 4 is just pi, we don't care. 5 pi over 4 is in quadrant 3. 6 pi over 4 is 3 pi over 2, which reduces. And 7 pi over 4 is in quadrant 4. Same thing for these ones. Pi over 6, quadrant 1, 5 pi over 6, quadrant 2, 7 pi over 6, quadrant 3, 11 pi over 6, quadrant 4. And all the other multiples of pi over 6 reduce to something else, right? 2 pi over 6 is pi over 3. And 3 pi over 6 is pi over 2, and 4 pi over 6 is 2 pi over 3, and 5 pi over 6 is the next one that doesn't reduce. And then 6 pi over 6 is pi, and then 7 pi over 6 doesn't reduce. 8 pi, 9 pi, 10 pi all reduce over 6, and then 11 pi over 6 is the last one. So it's kind of a neat little pattern. It always kind of works. So if you see something over 3 with a pi, you know the reference angle is going to be pi over 3. It's kind of great. So then, yeah, we got 5 minutes. I'm doing all right. Maybe. We'll see. We've only got 3 more pages to get through. Probably won't get through all of them. It's all right. Some of these examples I write just so that they're there in the notes so you guys can see them. So putting this all together, the whole idea is that since we know how to find the trig functions for the special angles, pi over 6, pi over 4, and pi over 3, and we know how to determine the sign based on the quadrant, we can use the reference angles of these other angles to find sine, cosine, tangent, whatever, of angles that have reference angles that are special angles. So for example, I want to find sine, cosine, and tangent of the following angles. Let's start with theta equal to 4 pi over 3. All right, so let me ask everybody, what's the reference angle? It is pi over what?
3.
Yeah, trying to wait, but also I'm trying to use my time. So here's the way I'm going to do this. Reference angle is pi over 3. If I need to, I can draw the triangle for that. Here's the triangle for pi over 3. Pi over 3 is the medium-sized angle, so the medium-sized side goes opposite of it. The hypotenuse is the largest side of 2, and this side down here, the small side is 1. So then I'm going to wait to look at the signs, S-I-G-N's. So I know that sine of, I'm going to write 4 pi over 3 and I'm going to fix it in a minute. So what's sine of pi over 3? It's root 3 over 2. What's cosine of pi over 3? It's 1 over 2. What's tangent of pi over 3? Notice I'm saying pi over 3, but I'm writing 4 pi over 3. Tangent of pi over 3 is opposite over adjacent, which is root 3 over 1. But now, what quadrant is 4 pi over 3 in? Quadrant 1, 2, 3, or 4? Quadrant 3. And so in quadrant 3, we know that tangent's positive. So this one's positive, and the other two are negative. And to me, that's probably the most efficient way to evaluate trig functions of angles that are bigger than pi over 2 or 90 degrees, is to find the reference angle, find the values based on that reference angle, and then determine the signs based on the quadrant that we're in. So let's do one more, maybe 2 more examples. So let's look at alpha equal to 3 pi over 4. I didn't even have to think about, since this fraction is reduced, right? I can't reduce 3 over 4 any further. There's no common factors. I know my reference angle is pi over 4. And I know my quadrant is what? You can show me on your fingers. You can be like, well, I just gave away the answer. Next time you can show me on your fingers. So quadrant 2. And so in quadrant 2, I know that sine is positive. So I'm going to say that sine of 3 pi over 4 is positive. Cosine of 3 pi over 4 is negative. It's not negative 1. And tangent of 3 pi over 4 is negative. And then I'm going to find the values in whatever way is most convenient. You might already know the sine of pi over 4 is root 2 over 2. That's fine if you know that. Or you might draw the triangle. Right? Pi over 4, it's 1, 1, and root 2. And then cosine is going to be the adjacent over the hypotenuse, which is 1 over root 2, which rationalizes to root 2 over 2. And then tangent is the opposite over adjacent, which is 1 over 1. But tangent's negative because we're in quadrant 2. Cosine is negative, and sine is positive.